Dear students, first, do you have any question concerning the recordings of chapter 8? Were you able to go over the recorded PowerPoint?
Yes, doctor. Can you please go over it again?
Okay, yeah, I will. Okay, so last time we started with chapter 8, and we have seen what are the desirable mold properties in order to conduct a casting process. We should check for the strength, thermal stability, collapsibility, and reusability of the mold. Now, we have different materials that can be used in foundry sand. So for example, you can use silica or silica mixed with other minerals because they are characterized by good refractory properties. So they can sustain high temperatures. And you know that during the casting process, you will pour your metal at relatively large temperature. This requires good refractory properties of the material constituting your mold. Now, small grain size are used for better surface finish. You know that whenever you want to control the surface of your final cast, sometimes you need to have curvatures. The shape will be, more you have curvature, you should be able to follow, to trap the profile. This is why the formation of small, you can have your mold at surfaces formed with small grain sizes. Now, large grain size is more permeable. It will allow gases to escape during pouring. So in general, you have to do a compromise between grain size of your material making your mold, because for small grain size, you can have a better surface finish, while you need also, yes?
Are you sharing the screen?
Yalla, let me check. Sorry, yes, now, do you see it now?
Yes. Thank you.
Okay. Okay, so we were talking about the properties of the material making your mold, okay? And we said that we can have it characterized by a large grain size and small grain size. Now, which one is better? In general, a combination of both is better. What we mean by this, so let's say you have a certain shape to produce, and the mold is constituted by a certain material. If you have a lot of curvature in your final design, you should have like small grains of your mold material in order to be able to capture these curvatures. Because if you imagine you have large parts, this leads to some voids. Okay, so larger are the grains part, you have some voids and some inaccuracy, and the accuracy of your finish will be reduced. However, the presence of large grain size in your mold material is also good because it will allow gases to escape during the pouring process. So in general, we prefer to have irregular grain shapes constituting your mold material, because this will, from one side, enhance the surface finish, and at the same time will still allow gases to escape during pouring. So this is what we call irregular grain shapes that will strengthen the mold due to interlocking effect compared to round grains. Now, the disadvantage of interlocking grains, okay, which increase the strength, but if you want to create some block for gas escape, is that interlocking reduces permeability. So in general, we try to have combination of all of these features if possible, not just small grain size, or not just large grain size, or not just interlocking grains. So sometimes, depending on the geometry we want to create, we create several zones characterized by different properties of grain sizes. Now, we always use also binders with foundry sand because you know that we need to hold the sand particles together. So sand is held together by a mixture of water and bonding clay. Now, the typical mixture is constituted by percentages of sand, water, and clay. And of course, the highest percentage is for sand. And the remaining part is water and clay, which will help to create adhesion between the different particles of sand. Now, we might sometimes add other bonding agents which can enhance the properties of your mold. We can add the organic resins, we can add inorganic binders, and sometimes we have additives that are combined with the mixture in order to increase or the strength or the permeability. So it depends on the final characteristics desired for your material constituting the mold. Now, we have different types of sand mold. The first one is called green sand mold. It's consisting of a mixture of sand, clay, and water. And whenever we talk about green, this means that the mold will contain moisture at time of pouring. So we have moisture within the sand because of a certain level of humidity, while dry sand mold is consists of organic binders rather than clay. So whenever you use clay, you should add water, and this will create some moisture in your mold. If you want to get rid of this moisture level, you should use other type of binders. So you can use organic binders. Now, in general, in this case, moisture will reduce the strength. So this is why when you bake your mold, you improve its strength. Now, we have also skin-dried mold, consisting of drying mold cavity surface of a green sand mold to a depth of 10 to 25 millimeters using torches or heating lamps. So sometimes, even if we have a green mold, we can do some surface treatment, okay, in order to enhance the strength of the surface. So this can be done by heating techniques that will give characteristic at the surface stronger than the remaining of the mold. And you know that the surface is the most critical part because it will be in direct contact with the object, which will give you the final pattern at the end. Now, what about buoyancy in a sand casting operation? During pouring, buoyancy of the molten metal will tend to displace the core because you know that sometimes if we want to have internal surfaces, we will need to place a core within the mold cavity. And then when you fill your cavity, this core will be subjected to buoyancy effects because you know from fluids that whenever you have a certain body immersed in a fluid and you want to study forces acting on it, you have the weight of the core and you have buoyancy effects that will oppose, if you want, that will try to get it up. Okay, so in total, we say that the buoyancy force, the net force on the core, if you want, can be estimated as what do we mean by WM? Whenever you have an object immersed in a fluid, the fluid will develop on it a force equivalent to the weight of molten metal displaced. Okay, so let's say you should compare the density of the core. So you have the core is characterized by a certain density, and your metal is characterized by a certain density. The upward force will be equal to the density of the metal used in pouring times the volume of the core. However, the weight of the core is rho of the core, the density of the material constituting the core, times the volume of the core. Now it depends which density is larger. This will create a certain net force or up or down. Okay. In order to oppose any displacement of the core, it should be hold as we mentioned before, we fix it through chaplets to the mold, to the mold body, and in this way we oppose any displacement of the core. So this is why when we design chaplets, we should know what is the buoyancy force acting on the core to be able to put chaplets that are able to oppose buoyancy effects. Okay, so we say that buoyancy is the force tending to lift the core, and it's calculated as the weight of displaced liquid less the weight of the core itself. Now, in case the density of the core is larger than the density of the metal, then the core will tend to move down. Okay, so you can have the buoyancy up or down depending on the difference of densities between the core and your molten metal. Christina, it's still lagging, or it's better?
No, it's better now.
Okay. So now we'll talk about other expandable mold processes. Already sand casting is one of the expandable possible mold processes, but we have a lot of other techniques that are expandable. Whenever we say expandable, this means that we need to destroy each time we produce a cast, we should destroy the mold. We have several types of mold of expandable processes: shell molding, vacuum molding, expanded polystyrene process, investment casting, and plaster mold and ceramic mold casting. We can go over all of these in detail now. The first type is shell molding. What is the idea here? In this system, the casting process is characterized by a mold, which is a thin shell of sand held together by thermostatic resin. Now, what are the different steps to do? The first step is the following. If you look at this figure, you have first a dump box. In this dump box, you put sand with the resin binder in order to hold the sand particles together. And then at the top of it, you have a heated pattern. So you should heat it to a temperature high enough in a way that when you reverse your box, the sand will be placed here, and due to heating effect, if you want, be adhesive to the final pattern. So this is the first step. First is to heat the pattern, and then the second step here will be, as we said, to reverse your box. When you invert your box, sand and resin will fall onto the hot pattern, and due to this heating effect, you will have the formation of a layer of the mixture to partially cure on the surface to form a hard shell. So a part of the sand here, due to heat treatment, will be will be adherent to the pattern and will form a shell around it. Okay, so you will give it enough time to form the shell you desire, and then once this is done, the box is inverted again, so it's repositioned in the initial position. So loose uncured particles will drop away, while particles that were, if you want, subjected to heat treatment will be adhesive to the pattern, and they will create a certain layer around this pattern. This will allow you to create thin, if you want, thin patterns of your final. If you desire to create a thin mold, this is a possibility to use shell molding. Now, the next step is that sand shell is heated in oven for several minutes to complete curing. So you can continue the process of formation of your mold by heating again in an oven. And after this, the shell mold will be stripped from the pattern, and in this way you will create a mold that can be used to produce such shapes. Okay. Now, once you obtain the desired shape, then you can do, for example, if you have a symmetrical object, you can produce two halves of the shell mold and you assemble them supported by sand or any metal shot in a box, and pouring will be accomplished. So as you can see, in shell molding, we produce this part which consists of a thin layer that will take the form of a certain pattern. And if you want to produce a symmetrical shape, you need to produce two shells, and then you should assemble them together. And once the assembly is done, you will also pack around these two shells if you want any material. It can be sand, it can be a certain metal. So just to be filled between the mold and the flask. And then you once you do this assembly, you created your cavity. This is your mold cavity here, which is determined by the surfaces of your shells. And now you are ready to accomplish the molding process. You can pour metal, and all other steps are equivalent or are similar to the ones we have seen before in sand casting. You pour your metal, you give it enough time to solidify, and at the end you destroy your mold in order to take out your produced system. So, for example, here, this is a finished casting produced by shell molding. And as you can see, in general, you have a symmetrical profile. You can easily you can easily have it by shell molding. All you have to do is to design these two parts separately, and then you assemble them to make your cavity, and use in this technique you will use shell molding to produce your mold. Now, what are the advantages of this technique? First, you can control better the smoothness of your surface. So a smoother cavity surface permits easier flow of molten metal and better surface finish. So to compare to sand casting, it will produce good dimensional accuracy, and the mold collapsibility will minimize crack in casting. Because of the heat treatment you created, you will have a surface that surface of your mold is characterized by a high strength, and this will reduce formation of cracks in the casting. And this system can be mechanized for mass production. Now, the disadvantages is that it's more expensive than having a metal pattern, and it's difficult to justify if you have small quantities of production. Now, what about vacuum molding? Vacuum molding is another type of expandable molding processes. It uses sand mold held together by vacuum pressure rather than by a chemical binder. We already said that whenever we want to have a sand mold, we should have a certain type of adhesive or binder to keep sand particles together. Now we can, instead of using a chemical binder, we can create this effect of adhesion between the sand particles by vacuum pressure. So in this case, we say that we are using vacuum molding. The term vacuum will refer to mold making rather than casting operation itself. So here, if you want these different types of techniques, rely on different ways of preparing the mold. Okay, but the other steps are nearly the same: the pouring, solidification, and extraction of the final product. So what are the advantage and disadvantage of vacuum molding? First, one of the advantages is that it will be easily, you can easily recover the sand. So once you destroy your mold, you can use sand again, because and already you don't have to separate sand from binders or do any additional treatment to use it again, because already you don't have binders in your mixture. Sand does not require mechanical reconditioning done when binders are used, so this is an advantage. And since no water is mixed with sand, moisture-related defects are avoided. Now, concerning these advantages, vacuum molding is a relatively slow process because you need more time. Instead of just adding binders to your mixture and having your sand particles adhesive together, you need to create vacuum. And creating vacuum is not very simple. You know that you need to, sometimes you might have some some pressure effects that will not allow perfect vacuuming. So the vacuuming techniques should be that is used are very sophisticated and they will cost a lot. So this is why this system is not readily adaptable to mechanization, because it requires complex techniques to be implemented. Now, what about expanded the polystyrene process? In this process will use a mold of sand packed around a polystyrene foam pattern, which vaporizes when molten metal is poured into mold. And we have a lot of names describing this type of process. We have the lost foam process, the lost pattern process. So as the name indicates, at the end, the pattern will be lost. It will be evaporated. It will not remain. So, so no need to destroy it at the end, because already during the process it will evaporate. And also we call this process full mold process. The idea is polystyrene foam pattern will be used, and it will include the sprue, risers, gating systems, and internal cores if needed. And the mold does not have to be opened into cup and rack sections. Let us see the details of this system. So these are the different steps. The first step is you bring, let's say, your pattern. Okay, your pattern will be constituted of all parts desired: the sprue, if you want the pattern of your cavity, how should be your cavity. What you do then is you bring a spraying refractory component in order to coat your refractory compound, in order to coat your pattern with a refractory compound, in order to sustain, if you want, very high temperatures. Now, next step, the foam pattern will be placed in mold box, and sand is compacted around the pattern. And now, when you pour your metal within your cavity, look what will happen. So molten metal will be poured into the portion of the pattern that forms the pouring cup and sprue. And as the metal enters the mold, the polystyrene foam is vaporized ahead, and the advancing liquid will fill the mold cavity. So here, what will happen is that the molten metal, if you want, will replace the vaporized foam pattern. So the foam pattern at small temperatures will have a solid, like a solid behavior. But when when in contact with very large temperatures, okay, they will vaporize, and then the molten metal will take their place, and this will allow you to create the shape desired, because the foam pattern will be replaced by your metal. Now, the advantages of such processes are that pattern will not, we don't need to remove the pattern from the mold. This will simplify and speeds up mold making because we don't have two mold halves, and this will not require to open the mold at the end. The disadvantages is that at each time a new pattern is needed, so we should have an economic justification of the process in order to go through it. Now, some of applications of such expanded polystyrene process, it's used for mass production of castings for automobile engines. And also automated and integrated manufacturing systems will be used to mold the polystyrene foam patterns. Yani first you need a certain effort to make your polystyrene foam molds, and then you will feed them to the downstream casting operation. But in general, this system, if you want, presents the advantage that you don't have to separate it into two parts, so you can directly create the whole system without having to dividing your mold into two parts. Plus, also you can have a good, you can control your curvature to a large extent, because with foam you can create any curvature you need. Foam is flexible; it allows you to make curvatures, to make complex geometries, etc. So as you can see here, for example, it's used to produce complex shapes as aluminum engine head, which is produced by expanded polystyrene casting process. So whenever we have very sophisticated geometries, it's a good strategy to use the polystyrene, expanded polystyrene casting process. Now, another type of expanded processes are investment casting, and it's called also known as the lost wax process. In this process, a pattern made of wax is coated with a refractory material to make the mold, after which wax is melted away prior to pouring molten metal. So the idea is here that we say investment, the term investment comes from a less familiar definition of invest, which is to cover completely, because the idea is to cover completely your material around a wax pattern. And this is a very precision casting process. It is capable of producing casting of high accuracy and intricate details. Now we'll see what are the different steps of this process. So, for example, you want to produce such geometry, which is relatively complex. So what you do first, you should produce the wax pattern, okay? And then you can attach to it several other patterns, so which will make the geometry more complex. So what you can do here, let's say you want to have several, you want to create at the same time several patterns. You just have a wax sprue, and you attach to it, to your sprue, you form a pattern tree. You can put several patterns at the same time. So let's say this is your object of interest. You can do the step, in one step you can produce several parts of your final product. Okay, so you attach your wax pattern to a wax sprue. This will form what is called a pattern tree. And then the next step will be to coat your pattern tree with a thin layer of refractory material. And then, as usual, the surface of the tree, the external surface of the pattern tree should be will be covered by a thin layer of refractory material to be able to sustain very large temperature. And then your full mold will be formed by covering the coated tree with sufficient refractory material to make it rigid. After this, the mold will be held in an inverted position. So as you can see here, we put it in inverted position and we heat it to melt the wax and permit it to drip out of the cavity. So the idea is that we have, as we said, this we have wax that is constituting the system here. And it is first in the solid shape. Okay, now since you already treated the surface with a refractory material, whenever you heat, the surface will be protected because it was already subjected to a heat treatment, so it will be able to sustain high temperatures without melting. However, the wax within this surface will melt under the effect of heat, and then this will, because you put your system in the reverted position, wax will get out of your pattern, and then you will be able to create a thin layer that forms the shape that you want to produce at the end. So the only remaining part will be a thin layer. Because of the heat treatment, because of the refractory material you use, this part will not melt, and you will obtain a thin layer that will give you the pattern desired. Then when wax is removed, now you can invert it back into the initial position, and your mold will be preheated to a high temperature, and the molten metal will be poured, and it will be left to solidify within your system. So you created a cavity of complex shape, and you can use now, after your metal will solidify, then you can you can trim these parts here, and you will obtain, you destroy pattern, you destroy your molds to obtain the final desired shape. So as you can see here, after you are done, your mold is broken away from the finished casting, and the parts are separated from the sprue. Now, as expected, this method allows to create a good surface finish and intricate geometries. So for example, one of pieces that can be produced using this method is a compressor stator. So as you can see, it's a very detailed geometries with thin layers. So this can be produced using this type of expanded processes. Now, concerning the investment casting process, it represents several advantages. So first, you can create parts of great complexity and with a lot of details. Of course, you can have closer dimensional control and good surface finish. And also, wax can usually be recovered for reuse. In addition, this is a nut shape process. So it's characterized by a high surface finish, and additional machining is not normally required, like in sand casting, for example. Now, concerning disadvantages, we have many processing steps to achieve the final product, and it's a relatively expensive process. So it depends on your application. If really it is worse, you can go through this type of casting. Now, another type of expandable processes is the plaster molding casting. It is similar to sand casting, except that the mold is made of plaster of Paris. So you are using another type of material, but as concept, it's similar to sand casting. In mold making, plaster and water mixture will be poured over plastic or metal pattern and allowed to set. And in this case, wood pattern will not be generally used due to extended contact with water. So to not have, let's say, problems related to humidity of wood. In this case, plaster mixture will readily flow around the pattern, capturing its fine details and will lead to a good surface finish. So it's true that it's similar to sand casting, but it's characterized by a better accuracy and better surface finish of the final product. So if we compare plaster mold casting to sand casting, it represents better accuracy and surface finish, and it's capable of making thin cross sections. However, the disadvantages are that mold must be baked to remove moisture, and moisture can cause problems in the casting. In addition, mold because of use of water. In addition, mold strength is lost if overbaked. So whenever you bake your mold, it should be very well studied, because you just should remove the moisture without overheating. The plaster molds cannot stand high temperatures, so they are limited to lower melting point alloys. This is another limitation. We cannot use them with any type of alloys. Another type is ceramic mold casting. It is similar to plaster mold casting, except that mold is made of refractory ceramic material that can withstand higher temperatures than plaster. It can be used to cast steels, cast irons, and other high temperature alloys. And its applications are similar to those of plaster mold casting, except for the metals cast. Now, for concerning advantages, they present a good accuracy and finish. So for the final part. Now, in general, if we talk about expandable processes, all share the same common disadvantage, is the one of the economical level, because at each time a new mold is required for every casting. So this is why permanent mold casting processes can be more used for mass production, but of course, as we said before, they cannot produce any geometry desired. So in permanent mold casting, we overcome this disadvantage of expandable molds, but at the same time we have other limitations concerning the geometry of the final product, because we are restricted by the fact that we want to, for example, to open the mold, or we don't want to destroy it, we want to use it again and again. So now we'll see what are the permanent mold casting types, and these processes include the basic permanent mold casting, die casting, and centrifugal casting. So to start with, we have the basic permanent mold process. Will use a metal mold constructed of 2 sections desired for easy, precise opening and closing. So we already have seen this. You have the cup and drag parts, and at the end you can open your mold to extract your final product. Molds used for casting lower melting point alloys are commonly made of steel or cast iron. Now, the material in which you fabricate your mold will depend on the metal you are used for casting. Whenever you have a lower melting point, you can go to a mold with steel or cast iron. However, if you want to reach very large temperatures, then you can use for casting steel made of refractory material. So you should do a heat treatment for steel in order to be able to sustain the very high temperatures of the poured metal. Now, let us see what are the different steps in permanent mold casting. So first, mold is preheated and coated for lubrication and heat dissipation. As you can see, always this step of preheating will give a certain strength for the surface of the mold, and it will allow it to resist the large temperatures of the during the pouring process.